Okay, so it's 11 o'clock. Welcome back to another session. Please, do you have any comments or questions before we start? Okay, so if there are no questions, then let's continue from where we stopped the last time. Please, I'm sharing my screen. If you can't see, do let me know. So let me see. Okay, you can see, right? I'm sharing a PowerPoint. Okay, if you can't see, do let me know. Now, the last time we're looking at continuity, right? Continuity. And we said that the function f is continuous at a point A or a number A if the limit as approaches of the function is equal to f of A. In other words, we use direct substitution to find the limit, right? So we saw that this definition is in three parts. The f of A has to be defined, the limit has to exist, and then the limit and then the function at A have to also be equal. So we established these, right? Now, the question that we actually looked at was the graphing one. So that one, we had a graph and we had to figure it out, like where the function is continuous and where is discontinuous. Now, the other thing we're looking at was this example, right? So example 2, this was where we left off. So for this one, I'm going to do it on the whiteboard, right? So let's do it on the whiteboard. New share. So this example 2. Okay, so for the A, we have f of x equal to, let me just write this down here. We have s squared minus x minus 2 over s minus 2. Now, we are asked to find where the function is discontinuous, right? Where the function is discontinuous. Now, from last time, we realized that if the function is continuous, it has to be defined, right? So for a function like this, what we are going to investigate is, let's try and see if we get a point where the function is not defined, right? If we have a point where it is not defined, then that means that the function is discontinuous at that point, right? So for this one, you can clearly see that since it's a rational function, and for rational functions, when the denominator is equal to 0, it is not defined, right? In any case, we get x equal to 2. So f of 2 is undefined. Hence, f is discontinuous at 2. Right? So that's how you figure it out. So for this one, we have to pay attention to where the function is what? Is undefined. Now, that is the reason why it's what? Is discontinuous, right? The function is undefined. But let's check the other conditions and see if the other conditions hold, right? So let's check the other one. So let's try and check the limit as s approaches to, since it's the candidate that we got here, right? That's where it is discontinuous. That's the point that we are investigating, like of the function. Now for this one, you realize that if you take the limit, s approaches 2, you have the expression as s squared minus x minus 2 over s minus 2. Now for this one, if you plug in 2, you're getting 2 squared, which is 4, 4 minus 2, which is 2, 2 minus 2 is 0, right? And then if you plug in, so this is going to give you something like type 0 over 0. So what do we do? For type 0 over 0, we try to simplify and then we plug in again, right? That's what we do. So for this one, let's try and simplify. What are we getting? You have limit as s approaches to, let's factor the numerator, right? So for the numerator, we have s squared minus x minus 2. So you're looking for two numbers whose product is negative 2 and whose sum is negative 1. And those two numbers are s minus 2 and then what? S plus 1 over s minus 2. And then at this point, from what we learned, we can cancel out these common factors, right? The s minus 2's cancel out. So everything reduces to limit as s approaches to of the function. Limit as s approaches to of the function is equal to what? So we have a limit as s approaches to is now going to reduce to s plus 1. And then at this point, we try plugging in again, right? That's the technique. So plug into, you get 2 plus 1, equal to 3. So that means the limit does exist. Limit exists, right? Okay. Now, the last condition is that if the limit exists, then the value that we are getting should be the same as the value that you get when you plug in. In this case, the function is not even defined, you see. But I'll just showing you this to emphasize that the limit exists here, but the function is undefined. And then the fact that the function is undefined is what's creating the discontinuity, right? So that's all. So the function is discontinuous at 2. So this is the conclusion. Please, any questions on this? Okay. Anybody needs time here? Okay. Oh, 1 sec. Okay. Nice. You're welcome. Okay, so then let me go to the next slide. So for the next one, we are looking at the B. So we are investigating the discontinuous part. And for B, we have f of x giving us, we have 1 over s squared if x is not equal to 0. And then it's 1 if x is equal to 0. Now, this is a piecewise function. For piecewise functions, where you have to focus on is where there's a break, right? So where is there's a break in a piece. So here we investigate at 0, right? At 0. So let's try and investigate at 0. The question is, let's pass through the 3 conditions that should hold for a function to be continuous, right? So let's check the first condition. Is f of 0 defined? What do you say? Is f of 0 defined? Anybody? Is f of 0 defined? Yes or no? What do you think? Okay, I have a yes. Perfect. Yes. Thank you, guys. Thank you so much. Yeah, f of 0 is 1. Perfect. F of 0 is defined, right? So that one is not a problem. Now let's look at the other case. Let's look at the limit as s approaches 0 of the function. So of f of x. So for the limit as s approaches 0 of f of x, right? The thing is, you're looking at s approaching 0. So 0 is here. We're looking at the function in the neighborhood of 0. So the question is, for piecewise function, you have to identify which piece of the function you're using for the particular limit. So the question is, if I'm taking the limit as s approaches 0 of the function f of x, right? Which piece am I going to use? Am I going to use the 1 over s squared or the 1? What do you say? Yes, I have 1 over x squared. Top one, perfect, right? Because the 1 over s squared is for when x is not equal to 0. So any number apart from 0. And then for limit, we are looking at the neighborhood of 0, not at 0. So that means that the piece of this function you're going to use is the 1 over s squared. Okay, so at this point, we try and calculate the limit, right? So the first thing we attempt is to plug in. Now, when you plug in, you're going to get 1 over 0, which is a type non-zero number over 0. So since it's a non-zero number over 0, and then this one is a limit, it's not one-sided. This is two-sided. It's not a one-sided limit. That means your answer possibilities are 3. You're either going to get negative infinity, infinity, or dn. Right? So let's try and investigate that and see. Right? Since it's general, we will take it from the right. So we take it one-sided. So let's do from the right of 0. So from the right of 0, let's look at 0, right? From the right, which kind of numbers are to the right of 0? We are looking at something like 0.000001, right? And that 1 over 0.001 squared, 0.001 squared will still give you like a 0.00001. So that is yielding what? Infinity. Please, are you okay with that? Do you see that? Okay. Now, what about from the left? So from the left to, we have 0 here from the left. So we are looking at a number like a negative 0.000001 of some sort, right? A negative 0.0001. Now, if you should put in these values that you are seeing here in this, because there's a square, it will turn the negative to positive. So you still end up with a 1 over positive 0.00001 of some sort, and that's still going to give you infinity. Now, in this case, since from the right and from the left are agreeing on infinity, we conclude that what? As s approaches 0, the 1 over s squared equal to infinity. Right? But recall that if the limit is infinity, then the limit still does not exist. And that's the language that we need here, right? So the second condition for continuity has been violated. The limit does not exist, right? So we can conclude that what? F is discontinuous at 0. Now, the reason for it not being continuous is not because the function is undefined. The function is defined, but the reason is because the limit as you approach the 0 does not exist. Please, are you okay on this? Any questions? Okay. Anybody needs time on this slide? Now, the PowerPoint will have the graph, so you will look at those two and see how they look like. But if anyone does not need time, let me just move on to the next one. So let's look at C. C is just A, but this time the function is defined at 2. If x is not equal to 2, 1 if x is equal to 2. Okay, so as I said, for piecewise functions, if you're investigating where the function is discontinuous, you have to focus on where there is a break. So here there is a break at 2. That's where we have a difference in functions, right? The break is at 2. So let's investigate this, right? So let's try and get the function at 2. Is the function at 2 defined? What do you say? Is the function defined at 2? Is f of 2 defined? So I have, yes, 1. Perfect. Perfect. Thank you so much. Yeah, f of 2 is equal to 1, right? Recall that the function is 1 if x is 2. So f of 2 is defined, right? So f is defined at 2. Okay, so that one is not giving us any issues. Now, the next thing we're going to try is, let's get the limit as s approaches 2 of the function, right? And similar to what we saw in the previous piece, because you're looking at the neighborhood of 2, the function takes on the form s squared minus s minus 2 over s minus 2 when you are in the neighborhood of 2. So that's the piece of the piecewise function you're going to use here for this limit. So you have s squared minus x minus 2 all over x minus 2. Right? So at this point, let's try and evaluate this. The answer is going to be the same as what you had in A, right? So you're going to get a type 0 over 0. If you plug it in, you're going to get type 0 over 0. It's the same as this one. Where is this? This one, what we did here, the same as this. So we can probably jump to the answer, but still, let me just go over this. So s minus 2, here you factor the 2, you get s minus 2, s plus 1 over s minus 2. So everything reduces to what? The limit as s approaches 2 of s plus 1 and equal to 2 plus 1, which is 3, right? So that means the limit exists, right? The limit exists. Now, the last thing we have to check it is the limit as you approach 2 of the function equal to the function at 2. Well, you can see that the function, the f of 2 is 1, and then the limit as you approach 2 of the function is 3. So the two are not the same. So this condition has been violated. So we conclude that the function is what? Discontinuous at 2, right? And the reason for the discontinuity is because the limit and then the value of the function at the 2 are not the same. They are not equal. So that's the mathematical reason. Please, any questions on this? Anybody needs time here? Okay. Then let's move on. Now, the last thing we are going to look at is, now these examples have been chosen for a reason, right? You see the reason very soon. They've been chosen to illustrate that the 3 types of discontinuity. So D, you're looking at f of x equal to This one's called the greatest integer function or the floor function, right? So something like this, that's the notation. Okay, so let me name this. This called the greatest integer function. Or some also call it the floor function. So the greatest integer function returns the integer less than or equal to an x, right? So let me give you some examples to illustrate this. So suppose you're asked to find the greatest integer for, say, 2.6. Then the integer less than or equal to 2.6, the greatest integer less than or equal to 2.6 is 2. So that's why we have it as a floor function. You don't round up, you just take the floor value, right? The floor integer value, right? So this one 2.6 is going to be 2. The greatest integer for 2.7, right? So this for 2.89 is going to be what? 2 still. The same thing for 2.1 is still going to be what? It's a floor function, so it's still 2, right? What about this one for 2? That one is still going to be odd. So the greatest integer less than or equal to this 2 is still 2, right? Okay, so if you understand that now, can you please help me with this? So what about this? Say 1.9, what would this be? Anybody? What's the greatest integer value for this? Okay, I have one, perfect, thank you, that's true. Okay, now let me make it a little bit tricky. What about this one? Negative 3.5. What do you think? Negative 3.5. So I have negative 3. Do I have a different answer or a seconder? Negative 3. Okay, thank you. So for this one, the greatest integer for this value is rather negative 4. Wait, but it will be 3 because it's absolute. I'm confused by the 2 times 1. Is it 2.1? Do you mean 2.1, Mackenzie? Okay, yeah, so the 2.1, as I say, is a floor function. Maybe this one will help. Let me do a little like number line, right? So say this is 2, this is 3. For any number between this, right? Any number here, not at 3, any number less than 3, right? Up to 2, will always go back to 2. Will always floor it to 2. You see, so 2.1 is in this interval, 2.3 is in this interval, 2.6 is in this, 2.9. As long as we don't hit 3, everything will reduce, will floor back to 2. Right? Now, let's look at the negative 3.5 thing, right? So don't forget the definition of the greatest integer. Is the s value, is the greatest integer less than or equal to the s value, right? So say for negative 3.5, we have negative 3 here. Say negative 4 is to the left of this, right? So let's say negative 2 is also here. Now negative 3.5 lies somewhere here. Negative 3.5. So what is the greatest integer less than or equal to this? The greatest integer less than that is negative 4. Do you see? So that's why I said this was tricky. You have to be cautious with the negative because we floor, we push it back, right? Yeah. Please, are you okay with this? Does it make sense? Okay, perfect. So that's the greatest integer function or the floor function. Okay, I'll have to move on to give you a graph. So for this one too, let's investigate where is this continuous. To see where is this continuous, we have to get a graph. So let me do this here. Let me do it. I think I'll get space here. So there's the x-axis, my y-axis. This 0 origin. So 1, 2, 3, 4. Negative 1, negative 2. And let's say this negative 1, negative 2. And that's 1, 2, 3. Okay, so let's look at how the graph will be. Let me use green to like differentiate it. Okay, so now let's go. So between this interval from 0 to 1, right? Any number that's false here is going to be what? It's going to be floored to 0. At exactly 0, the value of the greatest integer is 0, right? Because 0 is an integer. Wait, I thought they were multiples too. So every time these will go back. Yeah. Every time they'll go back to the lower valued number. Yeah, they'll go back to the lower valued number, right? Yeah, they'll be the same if it's the x itself is an integer. So say the greatest integer of 2 is 2 because the greatest integer less than or equal to 2 is 2. Please, are you okay with that? Oh, okay. Mackenzie, are you still okay or you have questions? Okay, if you do let me know. Okay, perfect. So now let's go. So as I was saying, we are trying to get a graph, right? So between 0 and 1, if it's 0, then it's 1. For greatest integer, if the value in the symbol is an integer, then it's that number, right? So the greatest integer of 1 is 1. The greatest integer for 2 is 2. The greatest integer for 3 is 3. The greatest integer for -1 is -1. For -2 is -2. What about in the interval? So between this interval, for any number in between, for like greater than 0 but less than 1, we will floor it to 0. So that means the graph lies on this line, right? It lies on the x-axis. It's 0 for any number here. And then at 1, we have a punch tool because at 1, we read the value at 1. The greatest integer for any number between 1 and 2. So if it's greater than 1 but less than what? Less than 2, then it's going to be shifted to 1. We'll floor it to 1. So that means that one is also flat like so. And then at 2, we rather read the value here. So that's a punch tool at 2. The same will happen for any number between 2 and 3, a number greater than 2, less than 3. That one too will be floored to 2, right? So that one too will be here, like so. It will be flat, horizontal, up to 3 where you have a punch tool. So you see this pattern going on, right? So like so, the same pattern, like the same will occur for the negative side. For any number in between the -1, so if it's greater than -1 but less than 0, then the floor function will take it to -1. So that'll be flat here. At 0, the value, you read it at 0. So you have a punch tool here, like so, and then like this. So that's the greatest integer function. So let me name it f of x equal to, with that symbol. Please, are you okay? Any questions? So that's the graph of the greatest integer function. Now for the greatest integer function, the question is, let's investigate where is discontinuous. So as you can see, the function is defined at every x. At every x, you get the value of the function. So there's no case. Is there a ceiling? Yeah, there's a ceiling function. Yeah, Donovan. Yeah, there's a ceiling function. So for this one, you see that the function is defined. So that's not it. You will not get any condition violated on the first point, right? The function is defined everywhere. Now for the second case, let's check the limit, right? The question is the limit as you approach any number exist? Is it going to exist? Well, as you can see, at every integer point, at 3, at 2, at 1, at 4, at every integer point, you notice this, you notice that the limit is what? Is DNE. The limit does not exist, right? Yeah, feel free to ask questions. Yeah, I don't know. So the limit is DNE. Because as you can see, say, let's take from 2. For 2, from the left, the limit is 1, right? And then from the right, the limit is 2. So the limit does not exist, right? So for here, it does not exist. For here, it does not exist. For any integer value, it does not exist, right? So that means for this one, the function is discontinuous at every single integer value point. Please, are you okay? I hope that makes sense. So it's discontinuous at every integer. At every integer. Please, are you okay? Any questions on this? Okay, don't worry about graphing this. You get a nice graph on the PowerPoint, right? Yeah. Anybody needs time here? I want to show you the result on the PowerPoint, and then we talk about all the discontinuous things you've seen. Okay, then let me go. Okay, so we are back on the PowerPoint. So for these 4 examples that we saw, the first one, you see the answers are here. Notice that f of 2 is not defined. So the function is discontinuous at 2, right? So that's for A. For the B, the limit does not exist, right? So the function is discontinuous at 0. For C, even though f of 2 is defined, the limit and the value at the point are not the same. So the function is discontinuous. It's not continuous at 2. For the greatest integer function, the function does not exist if n is an integer. Sorry, the limit does not exist if the n is an integer. So that means the function is discontinuous at all integers, right? So this is the graph that we are seeing for each of these functions. For A, we have this, right? So you see that the function is continuous everywhere except at this point where there's a point show. That's where the discontinuity occurs. Now for this one, you see that the function, the limit does not exist. What do you see? If you are looking at the geometrical sense, when you graph it, it's continuous, and then when you get to 0, you have to take your pen from paper, plot this point, and then move here. So it tells you that it is continuous at 0, right? But the fact that this one involves an infinite limit. Okay, what about this one? This one too is similar to what we saw for A, except that this one is defined, but it's just one point that's creating the issue. It's just this point. This is the point that's creating the issue. Now, for the greatest integer function too, you see this, right? Is discontinuous here. As I said, these illustrate the 3 types of discontinuity, right? The parts A and C are what we call removable discontinuity. Removable discontinuity. Now, why is it called a removable discontinuity? Well, the name is kind of direct. It's removable because you can kind of remove the discontinuity by defining a single point, right? So what I mean by that is, suppose for this one, right? If I define the f of 2 to be exactly that point on this point show, then it's continuous now, right? What about the C? Yeah, if I should just define this here to be that point, if I kind of like push this point here. So if I'm defining f of 2, I say f of 2 is say 3, right? Which will be this point. Then that means the function is now continuous. So it's removable because you can remove the discontinuity by just defining the function value at a single point, right? So that one is called a removable discontinuity, right? Okay. Now, what about the other one? Now, part B is what we call an infinite discontinuity, right? So this one is an example of an infinite. Why? For this one, we are getting a limit which does not exist because it's related to an infinite limit, right? It's related to an infinite limit. So that's how you know it's what? It's an infinite discontinuity. Recall that we learned that if it's infinity, then it does not exist, right? So this discontinuity which is created by an infinite limit. Do you see? So that's why it's called an infinite discontinuity. This is not like a removable discontinuity because you can't define it as a single point to make it continuous again. So that's what this one. Now for D, it's called a jump discontinuity. But this one is funny. You can think of it like some stairs. This is a step function. So you are jumping from point to point, right? You are kind of like jumping on these. So jump discontinuity. But then the mathematical reason is that the limit does not exist. And what is creating the limit that does not exist is not an infinite limit, but in this case, it's rather the one-sided limits are not agreeing on an answer. You see, so that's a type of a jump discontinuity. Please, I hope you're okay. So these are the 3 discontinuous types. Any questions on them? Okay, so that's it. The C is what we call removable discontinuity, right? Removable discontinuity, because you can just define at this point and then you have a continuous function. You see, so that's why it says, I think it's stated here, yeah, A and C. Okay, please, anybody, you're welcome. Anybody with any question here?
I have one question about the jump discontinuity. Could you go back to the last slide?
Okay.
So the one on the left is considered jump discontinuity, right?
The C?
Yeah.
This is the one. No, the right, this is the D. The D is the jump discontinuity.
Oh, I meant to say C.
Oh, yeah. So the C is removable because you can define it at one point. If I define it, this point here, if I should define it here, right, which is this value, it's going to be 3. Then it's now continuous. Do you see it now? So that one is removable.
Okay, thank you.
You're welcome. Please, any questions? Any other questions here? Okay, then let's move on. Now, just as we have continuous in general at a point, we can also have one-sided continuity. So a function is continuous from the right if this time around you're not looking at the two-sided limit, right? You're not looking at the limit as you approach from the two directions. You're looking at from the right or from the left. So we can have the function to be continuous from the right at a number a if the limit as it approaches a from the right of the function is equal to f of a. Don't forget, for this one too, it holds with the same three conditions as you saw here. It's the same three conditions, right? The only thing that will change is this time the limits involved will be either one-sided, right? Either from the right or from the left, right? So that's one-sided continuity. So let me get a quick graph, illustrate this. So let's say here is say 0, here is -2, here is 1, here is 2. So let me show you this. So for this one, at -2 is punctual. And then at 1, let me say I'll shade it here. And then I'll continue from here. And then at 2, I'll do this, open here, then shade it here, and then continue. So this is just a quick view of what the one-sided continuity is about, right? So for this one, at -2, the function is, this one is not one-sided. It can't be one-sided because for one-sided continuity to hold, the function has to be defined at a point. So at -2, this one is discontinuous. No matter what you do to it, it's still discontinuous. What about at 1? At 1, as you can see, the limit as you approach 1 in general does not exist because from the right and from the left are not equal, right? From the right, you're getting a point somewhere here, and then from the left, the limit is also somewhere here. But let's investigate continuity from the right or from the left. Now, as you can see, the value of the function at 1 is somewhere here, right? The value of the function is this point, is somewhere here. Now, if you approach from the right, you notice that that limit is also the same number. So here, at 1 is what? Is continuous, right? So if you approach from the left, right? So it's going to be the same point, right? If you approach from the left. So it's continuous from the left. What about at 2? So at 2, you can see that, it's discontinuous at 2 in general. But then if you track the value of the function at 2, the value of the function at 2 is, this point, is here, right? Somewhere here. And then if you approach 2 from the right, it's also going to give you the same value, right? From the left, it's not the same, right? From the right, it's the same as the value of the function at what? At 2. So that means at 2 is what? Is continuous from the right. Please, do you understand this? So this is an example to illustrate continuity from one side. Please, any questions here? Okay. Anybody needs time here? And don't forget, I always post the slides and everything, so you don't have to copy everything. Yeah. You can make a brief notes, but so 2 isn't continuous from the left. Yeah, wait, 2. No, 2 is not continuous from the left because the value of the function is up here. The value of the function is here. This f of 2 is up here. And then if you track it from the left, that is giving you a value here, right? The limit of as you approach 2 from the left is this, is approaching this point 2. So that one is not equal to the value of the function at 2. So it's not continuous from the left. Please, are you okay? Does it make sense now? Perfect. Okay, any other questions here? Okay, so now these are the 2 prime ideas here. Now this other one is just trying to talk about how you can create other continuous functions when you're given some other continuous ones, right? So what this is saying is, the chat is blocking the thing here. Okay, so what you can say here is, so now what we can say here is, if you have f and g to be continuous functions, then we can create continuous functions from these 2, right? as follows. So the sum of two continuous functions is also continuous. The product of continuous functions is continuous. The difference of continuous functions is also continuous. The quotient of continuous functions is continuous as long as the value of the function in the denominator is not equal to 0. Right? G of A is not equal to 0 in the denominator. And then for 3, the product of a constant and some continuous function is also continuous. Right? So just note these. Right? So getting complicated continuous functions from simple ones. Okay. Please, anybody needs time here. These are just definitions on continuous stuff, like recreating them. Okay. Now, as you notice, right, for continuous function, we just do direct substitution. You just plug in and you get your answer. You get your limit answer, right? So it's a good idea to know which ones we can do the direct substitution on, right? So any polynomial is continuous everywhere. So for polynomials, they're always continuous everywhere. And then any rational function is continuous wherever it's defined, right? As long as the point is in the domain of the function, then it's going to be continuous at that point, right? So that's what these two talk about. And then you see that there's not only polynomial or rational functions. There are also several functions which are continuous for any number in their domains. You look at that on slide 19. Yeah, but any questions here? These are things that you just have to keep in mind so that when you encounter them, you know that you just be plugging in. But even if you have no idea of the function, a continuous function is when you are taking the limit and you plug in and you don't get any undefined situations. Then that's it. That's the function is continuous at that point. Please, any questions here? Okay. Now, these are just illustrating examples of the polynomial functions, which are continuous everywhere. So as you know, the volume of the sphere is given by 4/3 pi r cube. So this function is continuous. Why? Because this expression you see here is kind of like a polynomial. It's a polynomial, right? In the same sense, displacement is also a continuous function. So for an example like so, you see that this is also a polynomial, which is continuous everywhere. So what that we are trying to say is for this one, whenever you're taking the limit approaching any number, you just end up plugging in. Okay. So they are just examples. Now, this was the group of functions that I was talking about. As long as the value of the x point is in the domain of such a function, then the function will be continuous at that point. So you see polynomials, trigonometric functions, exponential functions, rational functions, root functions, inverse trigonometric functions, and logarithm. As long as the number is in the domain, then the function is continuous. So essentially, just plug in and you get your answer, right? Direct substitution. Okay, sometimes you can have composite functions, whereby the outer function is continuous at the limit of the inner function. So if you are taking the limit of the composite function, you just be taking the limit of the inner function and then evaluating the outer function on that answer. But usually what I like to think about this is you usually end up just substitution, doing direct substitution, right? So that's a composite function and then continuity on this. Please, any questions here? Okay. So these are just definitions and more definitions, right? Another thing is if G is continuous at A and F is continuous at G of A, then the composite function is given by what? The composite function given by this is continuous at A, right? So as long as the inner function is continuous, the outer function is continuous for the limit of the inner function, then you just end up doing direct substitution for the composite function. Okay, so now with all these definitions, right, let's just move on to these examples. So let's try this. Now, these are some of the easiest questions you ever get because you're just doing direct substitution, right? Just direct substitution. So let's try A. How do these look like? So we have limit as s approaches -2 of s cubed plus 2s squared minus 1 over 5 minus 3x. So for this one, we try, okay, what is the first thing to attempt? Well, let's try direct substitution. So you have -2 to the 3 plus 2, -2 squared minus 1 over 5 minus 3, -2. Right, so that'll give you -2 cubed is -8. And then -2, that's 4, and then this is 8. And then minus 1 over, that's 5, and then this one is, this question looks familiar. It's kind of like we've seen this before, right? It's 5 plus 6, that's 11. So this will give you what? It's just -1/11. Now, because we didn't have any undefined cases here, you can see that this -2 is in the domain of this rational function. So the function is continuous at what? At -2. That's why when we plug in, we get the direct answer. So we are done. Please, are you okay with this? Okay. Can you please try to, please try the, sorry, not to the B. Please try the B. When you're done, give me your answer. And then we work it together. And then after that, we will do the C together. Yeah, so at least try B. Please try the B and let's see. Please, when you're done, feel free to send me. Nice. I have some answers coming in. So I have 1/2. Perfect. Thank you, Leo. Thank you so much. A different answer? So we have half, a different answer or seconder? Oops. Half. Perfect. I have a seconder. Okay, I have 0/, yeah. So at least I have a seconder to one of them. So let's just do this together. So for B, remember for continuous, you are just plugging in, right? So for B, we have limit as s approaches pi, and then sine of x over 2 plus cosine of x. So what do I try? I try plugging in. So I have sine of what? Pi over what? 2 plus what? Cosine of pi. Right? But the thing is, what is sine of pi? What is sine of pi? Sine of pi, yes. Sine of pi is 0. Right? So we have 0 over, what's cosine of pi? What about cosine of pi? Anybody? So I have 1. Okay, so -1, -1. Wait, yeah, -1. Right, cosine of pi, that's -1. So you're getting something like 2 minus 1. And what is that? That's just 0. Right? And this one didn't give us any issue. So that's our final answer. Please, are you okay with this? Any questions? Okay, then let's do the C together. Oh, anybody needs time here? Anybody needs time? I think I see something. So the numerator can be 0, but the denominator can't. Yeah. Because 0 over a number, like a non-zero number is 0. That one, no problems. Right, so our answer is 0. Okay, then let's continue with the C. So for C, we have limits as s approaches 1 of arc sine. So arc sine of 1 minus square root of x over 1 minus x. So how do you get this? Well, we first try direct substitution. So arc sine of, we have 1 minus square root of 1 over 1 minus 1. Oh, wait. The function is not continuous here. I think there's a typo here. Let me tweak this a little. This is supposed to be 2. All right, let's try 2. So let's try 2 here. Yeah, so you get something like this, right? So what are you getting in the long run? So I have arc sine of 1 minus 1 is 0, 0 over 1. So you have something like arc sine of 0, right? Which is sine inverse of 0. Sine inverse of 0 is just 0. That one too, no issues. Please, are you okay with this? Yeah, so for continuous functions, you just end up plugging in without it coming up with issues. So that's a continuous function. Please, any questions here? Okay, anybody needs time here? Okay, then let's continue with intermediate value theorem. So for this intermediate value theorem, it's sometimes useful for like finding if there is a root of of a function, right? If there's a root of a function. So let me talk about this. Now for intermediate value theorem, suppose a function f is continuous on a closed interval, right? So we have it continuous in a closed interval. Let n be any number in between the f of a and f of b, right? Okay. Now the f of a must not be equal to the f of b. Now if we are looking at this with a condition, so the function defined on a closed interval and then the f of a is not equal to f of b, then there has to be a number c in between the a and b such that the f of c equal to the n, right? So this one can be seen easily with the graph, right? So with these two graphs, you see that the blue line is continuous, right? You don't see any punched hole, you don't see like some separated parts. Or in the geometric sense, you don't see that we are going to lift our pen from paper when you are graphing this, right? So it's continuous. Now the f of b is given here. This is the f of b. And then the f of a is a point down here. Now, let's try and pick a point n, which is in between the f of b and the f of a. Now, as you can see, if we have a point n here, then there has to be at least one c in between the a and b, such that what? That the f of the c is equal to n. And you can clearly see that this is the case, right? So for this one, if we track the n to the curve, you see that this is the point c, which will give us the n. You see? So the f of c. And where is the c? The c is in between a and b, right? So that's what the intermediate value theorem is saying. Okay, now this thing holds. Let's look at this other case. So for this one, the function is continuous, right? So if we pick a number n in between the f of b and f of a, then by the intermediate value theorem, we should get at least one c in between the a and b, such that the f of that c is the n. And you can clearly see that this is true. In this case, we got like 3 c's. So C1, C2, C3, where the f of these c's, so f of C1 is f of C2 is f of C3, and it's equal to what? N. And these c's are in between the a and b. So that's what the IVT is saying. The proof is beyond this class, but here we just have to understand it using the graphs, right? So it makes sense. Are you okay with this? So that's the intermediate value theorem. Any questions here? Okay. Now this is still going to give us a different kind of graph, right? So these two, one was like a little increasing, decreasing, and increasing overall. They are kind of like moving up. The same goes with a function like this, right? If it's going down, the fact that it's continuous and then the f of a is not equal to f of b. If you're trying to find an n in between the f of a and f of b, then there has to be at least one c. So in this case, the c is here. The c is here. It's a point in between the a and b such that the f of c equal to n. Please, are you okay with this? Okay. So someone will ask, why do we need this? Well, to show why we need this, the importance of this, let's look at a problem here. Question, example 4. So for example 4, it says, show that there is a solution of the equation 4x cubed minus 6x squared plus 3x minus 2. So for this one, before you even solve it, you can get an idea if this equation will have a root or not, right? Will have a root or not, whether there's an x which we can plug in to get 0. So first, note that f of x is equal to 4x cubed minus 6x squared plus 3x minus 2, right? You are trying to solve this equal to 0, right? You're trying to look at f of x as some x which makes the function 0. Okay, now how do we know this x will be in between 1 and 2? Okay, so now let me plug in 1. If I plug in 1, I'm getting 4 1 cubed minus 6 1 squared plus 3 1 minus 2. So what is this? That'll give me 4 minus 6 plus 3 minus 2, which is equal to what? F of 1 equal to what? 4 minus 6, that's negative 2, so that's negative 1. Okay, what about f of 2? So f of 2 is 4 2 cubed minus 6 2 squared plus 3 2 and then minus 2. So what is this? That's for this 2 cubed maybe I can do some quick math here. Let me do 4, this 2 cube, that's minus 3, 2 cube, and then plus 3, that's 6 minus 2, that's 4. So this will give me 1, 2 cube, and then 4 minus 3 is 1, 1, 2 cube plus 4. So that's going to be 8 plus 4, which is 12. Now, you can see that f, the function is continuous, right? This is a polynomial. The f of s, which is this, is a polynomial. Polynomials are continuous everywhere. And then the value of the function at 1 is -1. And then the value of the function at 2 is 12. So that means that if you're looking for the value of the function, some s, which is 0, right? Then the 0 is in between the -1 and 12. Hence, there has to be an x in between the 1 and 2, such that the f of s is 0. Please, are you okay? So this shows that there has to be what? A root in between the 1 and 2. I see something in the chat. Yeah. No. Okay, thank you so much. Yeah, it's 11:50. Yeah, so I think we'll end here. Please feel free, if you don't understand anything, to send me an email, schedule an appointment. Right, so that's the end of 2.5. Next time we meet, we'll be looking at 2.6. And you have a quiz tomorrow, right, at recitation. So all the best. Thank you for your time. Yeah. You are welcome.
Thank you.
Thank you.
Thank you for your contributions as well. Yeah, you're welcome. See you on, today is Wednesday. Yeah, see you on Friday. You are welcome, guys.